Hi everyone, welcome back. So today we'll move on to lecture 21, which is on rectangular waveguides. So in the last lecture, we looked at TE-TM modes and dielectric waveguides or dielectric plate waveguide. Today we want to take it further into metallic waveguides that have a rectangular cross section. Okay, so essentially, let's say if I have a general cross section, which is PEC, right? PEC boundary. Then we want to establish boundary conditions on the potential rather than having to deal with the fields. And these boundary conditions are the Dirichlet and the Neumann boundary condition. Okay, so we want to derive them. Okay, so if you consider the TM case, then we know that the electric field in the z direction is given by AC square psi of x comma y e to the I beta z. Because it's TM, it has an EZ component. And of course, EZ must go to 0 at the boundary because it's PEC, right? So tangential EZ is the tangential component or one of the tangential components of E. And since that must go to 0 on the boundary, implies that psi of x comma y must be 0. Right? So setting psi equal to 0 is a necessary condition for EZ to be 0 on the PEC boundary. And therefore, this is an equivalent boundary condition of the potential. So this is called the Dirichlet boundary condition for PEC. Okay, so essentially when you substitute psi equal to 0, EZ goes to 0. So we satisfy the boundary condition for the TM modes on the surface of the PEC. Okay, similarly for TE, we have n hat cross E is equal to I omega mu n hat cross transverse gradient of psi m cross z hat e to the I beta z, right? So here we have a triple cross product and you can use the back cab rule and that will give you one term which is n hat dot z hat and that's 0 and another term which we're going to write down now. The other term is minus I omega mu d psi m over dn e to the I beta z hat. Okay, that's the directional derivative. N hat dot gradient is nothing but d psi over dn, right? That's the directional derivative along n. Okay, and this must be 0 because for TE modes, n hat cross E gives you the tangential component of E, and that must be 0. Right? So an equivalent condition is to set d psi m over dn equal to 0. So this is called the Neumann boundary condition. So these are essentially boundary conditions that we'll use when we are solving for metallic waveguides. By setting for TE modes, we set this boundary condition, and for TM modes, we set this boundary condition. Okay? So I'll call this the NBC, and this is the DBC. Okay, so given that we have these boundary conditions, now we can start looking at PEC waveguides. So the first one we'll look at today, and the most popular one in some sense, is the rectangular waveguide. Okay, so what does this look like? If I draw a coordinate system, say this is X, this is Y, and this is Z. Then the waveguide has a geometry that looks something like this. It's just a rectangular pipe, essentially. Excuse me. Okay. and I'll label some dimensions. So I'll call the width as A and the height as B. Okay, so you want to see what kind of modes exist in this kind of a waveguide. And what are the properties of these modes? So we start again with the wave equation, AC square psi of x comma y equal to 0. And the Dirichlet boundary condition enforces that psi 0 comma y must be equal to psi a comma y equal to 0. And also psi x comma 0 equal to psi x comma b equal to 0. Right? So x equal to 0 is this line must be 0. And then this condition corresponds to here and here, the field must be, the potential must be 0. So we'll start with Dirichlet boundary condition to solve for the TM modes. And the nice thing about this waveguide is that the walls are lined up with the coordinate system, the Cartesian coordinate system. So we can apply separation of variables. Okay, so we're looking for solutions of the kind x comma y equal to capital XX, capital YY. And later we'll show that these solutions are enough to represent any solution to the wave equation because they form a basis. So this is very similar to what we did in plane waves. So once you have this, you substitute this into the wave equation. And that gives you capital X over X, Y double prime plus Y double prime, Y over Y plus KC square equal to 0. Okay, so this is from the wave equation. And now, of course, we've said this before during plane waves, is that since this is a function of X, this is a function of Y, and they're independent, they both must be equal to a constant. Okay? X comma Y independent implies X double prime of X over X of X is equal to some constant minus kx squared. Similarly, Y double prime over Y equal to some constant minus ky squared. Okay, so that gives us the dispersion relation kx squared plus ky squared equal to kc squared. Okay, and then the solution to these two differential equations is pretty simple. It's the combination of sine and cosine. So we have a sine kxx plus b cosine kxx. And y of y is c sine kyy plus d cosine kyy. Of course, you can substitute these with these equations and see that they satisfy them. Okay, and now once we have this solution, we can apply the boundary condition. So the Dirichlet boundary condition implies what? X of 0 is equal to x of a equal to 0, right? Because psi is x times y. And similarly, y of 0 equal to y of b equal to 0. Okay? What happens when I do that? If I set x equal to 0, this goes to 0, and you're left with this term, and this goes to 1. So you have b. So then b must be equal to 0, right? Because when x is equal to 0, I should get 0. So this disappears, this becomes 1, and then you get b equal to 0. Similarly here, if you substitute this, then this disappears, this goes to 1, and you get this term equal to 0. Okay, so basically these two terms don't exist. And so let's maybe write that down. So implies that b comma d equal to 0. And now you can substitute the other part, which is this and this. And then you're left with sine kx a equal to 0 and sine ky b equal to 0. Sine kx a equal to 0 and sine of ky b equal to 0. So what does this imply? This implies that kx is some m pi over a, and ky is equal to some n pi over b, where m comma n belong to integers. Or you can say natural numbers, right? Okay. The reason I say natural numbers is that, okay, if you make it negative, then you still have the same mode, just with an opposite amplitude, right? So it's not really any different. Okay, so now I can write my psi mn x comma y, which is the function we were after, as a times c sine of m pi over a x times sine of n pi over b y, right? And I can combine AC into a single constant E naught. Okay, so this is my final expression for the aperture potential for a rectangular waveguide TM mode. Okay, it's sine times a sine. Beta Mn, which we define as square root of a square minus ac square, right? This is the wave number along the propagation direction z, becomes square root of square minus m pi over a square minus n pi over b squared. Okay. And of course, lambda g, which is the guide wavelength, which is the wavelength along z inside the waveguide, is 2 pi over beta mn. Okay, so note that, should say, different modes. So different modes corresponds to different values of m and n, have different beta and lambda, right? Which means the speed of light or the speed of the mode inside the waveguide is different for different modes, and also the wavelength is different for different modes. Okay, so what do these modes actually look like? So if I take the cross section, if I take my aperture of the rectangular waveguide to be something like this. Oops, try that again. Then I'll have a mode where it goes to 0 on both ends. Looks like that. Then I want a higher order mode. So this would be maybe the TM11 mode, right? And then the 2-1 mode may look something like that. So I'm just drawing what the electric field does over this aperture. Okay. And so on. So you can look up pictures of what these rectangular waveguide modes look like and the field distribution. And it's kind of fairly simple, right? It's some kind of sinusoidal thing in X and Y. Okay. So we can also write down the fields. So now that we have the potential, we can write down the fields. I E naught, beta Mn, m pi over a, cosine m pi over ax, sine n pi over by, e to the I beta mnz. Ey becomes I E naught, beta Mn, n pi over b, sine m pi over ax, cosine n pi over by, e to the I beta mnz, and Ez is E naught n pi over a square plus n pi over b square sine m pi over ax sine n pi over by e to the I beta mnz. And then you can also find hx and hy similarly, which I'm not going to write down just because I'm a little bit lazy. Okay. All right, so you can look them up in the textbook if you like. Uh, Moving on, you can define an impedance of the TM mode as Z hat cross E over H, or the magnitude of these terms. And that turns out to be nothing but EX over HY, or the same thing as EY over minus HX. And this turns out to be square root of K square minus M pi over A square minus N pi over B square over omega epsilon. Okay, and cutoff frequency is when beta Mn goes to 0, which means there's no propagation, right? So I can do that by going back to the equation for beta. I set this to 0, and that gives me a value of k, or a value of omega, or a value of f, at which that happens. And if you solve for that, you will get that the cutoff frequency is 1 over 2 times square root of mu epsilon, square root of m over a square, plus n over b square. Okay. Now, it's interesting to also note that for this kind of waveguide, m or n cannot be 0, because if m or n is 0, this whole thing becomes 0. You have sine times sine. Right, so the lowest order mode in Tm is Tm11. Right? Tm01, Tm10 don't exist. Okay. All right. So I should write that down. Tm11 is the lowest order Tm mode. Okay. Similarly, you can do the same kind of thing for Te, where you apply the Neumann boundary condition, and that gives you psi mn comma y equal to h naught, some other constant, which is determined by the excitation amplitude, or the amount of power carried in this mode, cosine m pi over ax, cosine n pi over by. Okay, so this is for Te. And the nice thing here is that you can have m equal to 0 or n equal to 0. Obviously, you can't have both equal to 0, because that doesn't give you a psi, it just gives you a constant. But when either m or n is 0, then you still have mode propagation. You have a non-zero psi, and you will have a modal solution. Okay, so the lowest order mode for Te is 10, or Te10, assuming A is larger than B. Okay, and the cutoff frequency of this, and this is actually called the fundamental mode, because this is the first mode that starts to propagate, because its cutoff frequency is the lowest. It's not 0 though, right? So below a certain frequency, it doesn't propagate, and we'll see that. Okay. All right, of course, you can find the fields and so on and so forth, or you can apply duality and get the fields for the TE modes, which I'm not going to do. But we can discuss something more interesting, which is the dispersion diagram. Okay, so what is the dispersion diagram? It's the relationship between the frequency and the wavelength. So sometimes it's called EK diagram in solid state physics. Sometimes it's called omega K diagram as well. Okay, they're all the same thing. So we're kind of interested in what is omega as a function of beta. So we have that k square minus beta square is equal to kc square, which is m pi over a square plus n pi over b square. And this is the equation for a hyperbola. right? So if I draw a straight line like this, so this is the straight line which represents light. It's called sometimes the light line, right? Or I can make it solid line. So essentially, the slope of this line and also the value at any point, if you take omega over beta at any point, that is equal to, so omega over beta is equal to d omega over d beta. Slope and value is the same because it's a straight line going through the origin, is equal to c, which is the speed of light. Okay, so on this, if you plot your, so let me use a different color. Let's say this is hyperbola. So on this, if you plot the waveguide for the lowest order mode, let's say it looks something like this. It starts from here and then it asymptotically reaches the light line. Okay. And a higher order mode would look something like this. And the higher order modes keep doing that. So they all asymptotically reach the speed of light. But interestingly enough, if you look at any point here, right, the omega over beta, which is the slope of the straight line connecting this point, is always greater than c. Right? So the speed of light looks like it's greater than c. For all the modes, at all frequencies, it's always greater than c. Right? And it approaches c at infinity. Okay, so we need to kind of address that because it looks like that breaks some maybe fundamental principles in physics where you can't have anything propagating faster than the speed of light. Okay, so in order to kind of establish this more formally, we need to define what is called phase velocity. Okay, so we know phase is given by omega t minus beta z is equal to the phase. So we want to see how fast this phase is propagating. So we take time derivative on both sides, right? So I take d over dt, both sides. That gives me omega minus beta dz over dt is equal to 0. And this dz over dt is exactly the phase velocity because that's telling you a single point in this wave as it's propagating. What is the velocity along z for that single point? Okay, so implies dz over dt is equal to omega over beta. That's exactly what we were looking at earlier, right? Different points, you pick a point, find what is omega over beta by finding the slope of that line, right? Or you pick a point, you take this, we take this divided by this. Same thing. This quantity is called the phase velocity. So this represents how fast the phase is moving along the z direction. That's the key thing. How fast the phase is changing along the z direction. Okay? U phase is dz over dt, which is omega over beta. I'm writing it down again here. It's the same thing. And this gives us a clue as to why it can be faster than the speed of light. So UP is always greater than C for all modes at all frequencies. Okay. Okay. So it doesn't break relativity, special relativity, because a single mode doesn't carry any information. And special relativity specifically says that information cannot travel faster than the speed of light. Okay. So another way to look at it is to say that, okay, if I have some wave propagating in this direction, this is my k vector, right? And I want to find out, okay, what is the propagation in some other direction? Let's say this direction. What is the phase propagation in that direction, right? So then basically I need to decompose my mode, my wave, into two parts. This one I can decompose into these two orthogonal components, right? So let's say if I have plane wave propagating in this direction, then the decomposition in this direction would be, if this is theta, k cosine theta, right? And I know v, speed of light or the phase velocity or in a given direction is omega over k, right? Which is nothing but c over, it's just omega over k, sorry. That's c, right? That's for plane wave in the direction of k. But now in a different direction, my k becomes k cosine theta. So it becomes c divided by cosine theta, right? And since cosine theta is less than or equal to 1, this will always be greater than or equal to c, right? So you can also look at this in another way. So if I have the same plane wave going in this direction, draw that again. So what's the physical picture? Plane wave going in this direction, which means I have phase fronts that are like this. Right? So my phase is propagating in that way, in this direction. But now if I look at a different direction, let's say I look at this direction, and I want to see how fast phase is propagating in that direction, then the phase actually propagates very fast, faster than the speed of light, right? Because this point moves to this point a larger distance in the same amount of time, right? So it moves, so this phase point moves to this phase point, which is a larger distance, but the time is the same. Same way, if you take it in this direction, then it moves from here to here, where this intersects this, in the same period of time, but the distance carried is larger, right? And of course, if you go in this direction, the speed becomes infinity, right? Because you're moving a very large, infinitely large distance in basically infinitesimally small time, right? So it doesn't mean that energy or information is propagating faster than the speed of light. Of course, energy itself is propagating fast like this, speed of light like this, but this phase actually moves very fast in these directions. Okay, and that's called the phase velocity. Similarly, if you take a waveguide, so in the waveguide, what's going on, right? I have my waveguide. We saw that these waveguide modes are nothing but plane waves propagating at different directions. Right? So I have a plane wave that's kind of going like this, maybe. We saw that in the last, do a better job at that. And you can represent it as the angular spectrum of different plane waves kind of bouncing back and forth. Right? And obviously, this goes at the speed of light in these directions. But we are looking at velocity in this direction. That was the phase velocity was defined along z. And we just saw that if I have a plane wave going in this direction, then the phase velocity in this direction is higher, right? Because in the same time covers a larger distance. That's why phase velocity along z is always faster than the speed of light. So this kind of connects it nicely back to that angular spectrum picture of waveguides, where we said that it's nothing but a discrete number of plane waves propagating in different directions. Right? And since none of them are really propagating along z, you'll always have phase velocity along z greater than the speed of light. Okay, so hopefully that's a nice intuitive picture as to what's going on. But we also want to establish another quantity called the group velocity. So we want to see what if I modulate information on top of this waveguide mode, then what happens to the velocity? And that is given by what is called group velocity. So what is the speed of modulation or speed of information? Okay. So the simplest case is if I take two tones, and see under this two-tone modulation, what happens, right? So I have omega 1 is omega naught plus delta omega, and omega 2 is omega naught minus delta omega. Okay, then my pi z, this is not the phasor quantity, this is the full quantity. So if you convert phasor back to space and time, then it becomes psi of x comma y cosine omega naught plus delta omega t minus beta naught plus delta beta z plus cosine omega naught minus delta. So I'm adding the two waves now. Minus beta naught minus delta beta z. So when I add these two waves, of course, you can use properties of cosines to write this as 2 psi x comma y cosine omega naught t minus beta z times cosine delta omega t minus delta beta z. To write that a little bit nicer. Times cosine delta omega t minus delta beta z. Okay, so this term is the carrier and this is the envelope. And the envelope is what carries the information. That's the modulation. So if you actually look at this wave, what does it look like? Maybe you've seen this before, right? It's a sinusoid whose amplitude is kind of modulated sinusoidally like that. Right, so that's the carrier. Maybe I should write this in blue. And this is the envelope. And it's the envelope that carries the information. So we want to see what happens to this envelope. So since this term represents the envelope, velocity of this envelope is given by delta omega over delta beta. And you can do the same kind of derivation that we did earlier. So UG, which is the group velocity, which is the speed of the envelope, dz over dt of the envelope becomes d over dt delta omega t over delta beta, which is nothing but delta omega over delta beta. Okay, and this was for a very simple case of just two-tone modulation. In general, this generalizes to d omega over d beta. By taking the limits. So this is the slope of the dispersion relation at a given point. So if you go back here to this picture and look at what the slope is, right? So at this point, the slope is like this. Slope is like that, slope is like that, slope is like that. Now the slope of the light line is the same. So in free space, if I have a plane wave, the information, phase, group, all of them propagate at the same speed. But inside a waveguide, note that the group velocity is always less than or equal to the speed of light. It's actually less than the speed of light, and at infinity, at very high frequencies, it becomes asymptotically equal to the speed of light. But at all of the frequencies, the group velocity is always less. And that makes sense, right? Because you can't have anything propagating faster than the speed of light. Especially, I mean, you can't have information propagating faster than the speed of light. Information is carried by the envelope, which is given by the group velocity. So essentially, the group velocity must always be less than the speed of light. And that's what we saw in the dispersion diagram as well. So physics is it's all working, right? Nothing is breaking. So you can also show that beta square, since it's equal to k square minus kc square, which is nothing but omega square over c square minus kc square. If I take derivatives, it becomes 2 omega over c square d omega over d beta is equal to 2 beta. Take derivative on both sides with respect to beta. And this is nothing but omega over beta times d omega over d beta. Right, so this implies that omega over beta times d omega over d beta is equal to c squared. Implies that the phase velocity times the group velocity is always a constant, c squared. And that also you can derive from the hyperbola condition. Right, so that's an interesting relationship. This is for rectangular waveguides. Okay. So now that we've kind of established the modes of the TM and TE modes for a rectangular waveguide, we looked at the dispersion relation and we showed the phase and group velocity. The last thing we want to look at is we want to show orthogonality of the modes and completeness rather. If you want to show that these modes form a basis, which is what we started with, orthogonality and completeness. So we'll show most of this today, basic ideas at least behind this, behind establishing that it's the basis. So we said that, okay, for a rectangular waveguide, these modes form a basis, and that's not very hard to show because essentially these potentials are sines and cosines, and we know sines and cosines form a basis, right? So if I have a 2D 2D problem, some kind of 2D structure, then sine in this direction, cosine in this direction, sine and cosine in this, sine and cosine in this, as this kind of a product forms a basis. That's easy to show from the orthogonality of sine and cosine itself. What we want to do here is to take it a bit further and show that we can establish orthogonality of modes for any arbitrary cross section. Okay, that's the hard part, and that's what we want to show now. Okay, so what do we want to show? We want to show that given psi m n, psi m prime n prime, they form, or I should say they form a basis in the fields, I should say. Okay. So given two modes, psi m and psi m prime and prime, the fields, EH fields that you get, form a basis, which means they're orthogonal and complete. So any solution of the wave equation inside a waveguide for an arbitrary cross section with PEC boundaries, we're only showing it for PEC boundaries, can be represented as a linear combination of these modes. Okay, that's what basis means. So we'll start with assuming that they satisfy the wave equation. Of course they do because they're solutions. So I have two different solutions for the wave equation. And these are two different modes. So mn is not equal to m prime and n prime is equal to 0. So what I do is I multiply the first equation with m prime n prime, multiply the second equation with mn, and then I subtract. Okay, so when I do that, I end up with psi m prime n prime into t square, psi mn minus psi mn delta t square psi m prime n prime is equal to k m prime n prime square minus k mn square times psi mn psi n prime n prime. Okay, nothing new here. We just kind of did exactly what I mentioned here. Now we want to integrate over the aperture of the waveguide and apply Green's second identity. Okay, so that essentially gives us that the left-hand side becomes contour integral psi m prime n prime d psi m over dn minus psi mn d psi m prime n prime over dn dl. Right, that's after applying the Green second identity. And this is equal to 0 because if I have TE modes, then this would be 0, this would be 0. If I have TM modes, then this would be 0 and this would be 0. Now, this does not guarantee that if I have one TM and one TE, this would go to 0, but that case we'll treat at the end. Okay, so right now we're assuming that we are looking at orthogonality between the TM modes or orthogonality between the TE modes. We're not yet establishing the cross orthogonality between TM and TE. Okay. Okay, so since that is 0, the left-hand side must then the right-hand side must also be equal to 0. Integral of this. Okay, so which means kmn or km prime n prime square minus kmn square times the surface integral psi mn psi m prime n prime ds is equal to 0. Okay, now of course this term is not 0 because we said that they are different. M prime, n prime are different, which means this must be 0. Right? So this is exactly the orthogonality condition. Okay? But this is not enough because we know that the electric and magnetic fields are given in terms of psi and also gradients of psi. So we also need to show that the gradient of psi is orthogonal. Okay, and for that we'll use the Green's first identity. Which is grad psi prime plus psi mn gradient psi m prime n prime ds is equal to contour integral psi mn d psi m prime n prime over dn dl. We know this is equal to 0 from the Dirichlet-Neumann boundary conditions. 0 from UBC and BC. This term here is minus kc square or kmn square prime n prime square times psi m prime n prime. That comes from the wave equation, right? So essentially this term must also be 0 because this I can pull out and then I end up with minus k m prime n prime square surface integral psi times psi m prime n prime. And we just showed that this is orthogonal, right? So this term must also go to 0. So this term is also 0. And that's exactly what we want, right? Because now we have this whole thing equal to 0, which establishes the orthogonality between the gradients. Okay? S is equal to 0. So this alone is not enough again, but we'll stop the proof here. You still need to show that this is orthogonal to this whole thing, and this is orthogonal to this whole thing. And if you do that, then that completes the proof because that establishes the orthogonality of all the fields. And if you want to establish cross field orthogonality of TE and TM, then you have to expand E and H in terms of the potentials, or one is TE, the other is TM. And then you can show from all of these orthogonalities that that is also true. Okay, so that's part of the book. I don't want to go into too much detail here. We'll stop it here because we're kind of running out of time. But you can look at section 6.8.1, which completes that proof. Okay. All right, so this is a good place to start. So we discussed the rectangular waveguide. Just to quickly review, we discussed rectangular wave, Dirichlet-Neumann boundary conditions, then the rectangular waveguide, potentials, we applied boundary conditions, we got the fields, we got the Kc or Kmn, and discussed TETM modes of the rectangular waveguide. Then we looked at the dispersion diagram and also what phase and group velocity is. And finally, we showed that the modes in general for a PEC waveguide for any cross section are orthogonal. Okay, and of course, completeness comes from the fact that you have an infinite number of these modes. Since you have an infinite number of orthogonal modes, essentially any field distribution can be written as a summation of these modes, right? Because you have an infinite dimensional vector space, you have an infinite number of orthogonal vectors, and that spans the entire vector space. So it is complete, and that's easy to show. Right, so in other words, you can write the coefficients of each mode as an inner product of the field distribution that you have with all the modes or given mode. divided by. So this is exactly how you get the coefficients of a given basis, right? So from orthogonality, you can easily show this. Okay. And any given modal distribution is written as summation over n, summation over n, amn, psi mn, x comma y. That's linear algebra. So essentially, you start from this, you take inner product with psi mn on both sides, or psi m prime and psi m on both sides, and then that will only give you one term out from here because of orthogonality. Okay, so we'll stop here, and in the next lecture, we'll look at for an arbitrary waveguide. For a rectangular waveguide, it's nice because it aligns with the coordinate system, but for an arbitrary waveguide, how can you numerically find what the field distribution and the propagation constant are? Again, that will introduce finite element analysis and finite element method, which is the big numerical technique that we want to discuss next. Okay, so hopefully you're excited about that. If you have any questions, you can leave them in the comments. If not, thank you, and I'll see you in the next one.